Hello and welcome. Today I wanted to talk with you and show you about a special subject about identifying the back EMF voltage of an PMS motor using the NDrive Oscilloscope. The back EMF voltage is not always known. A lot of motor manufacturers provide us with this information, but some do not. And the back EMF voltage, while it is not particularly necessary for controlling a motor, it is very helpful for the general control to be optimized. My system setup consists of a Bamocar 400/400 inverter and my Emrax 208 medium voltage motor. Of course, Emrax provides us with the back EMF voltage, in this case 0.0300 for voltage RMS per RPM. But like I've stated, a lot of times this information is not known to us. So I'm going to use the Emrax motor as a demonstration purpose to identify this back EMF voltage. Sometimes customers of ours, for example, believe they have an Emrax high voltage motor, while in reality they have a medium voltage motor. And via this test I'm going to show you now, you can actually identify which kind of motor you actually have. So for this demonstration purposes, it is very helpful to have everything already configured correctly, meaning you can actually control the motor as desired. So meaning the motor pole number is correct, the general configuration is correct, the motor pole as a feedback is configured correctly, and you can actually, as I'm going to demonstrate to you now, control the motor as desired, okay, by sending speed or torque requests. It is also recommended that you have a free running motor, and it is recommended that you limit the current output for safety purposes. So how we measure this back EMF voltage, in our case the KE constant, using the NDrive Oscilloscope? While this is very easy to do, it is a little bit complicated to actually do the procedures, but after a while you will see it's actually quite possible. On the NDrive Oscilloscope, I recommend to change the drop-down menu to motor, because we can actually see the KE factor for us to configure. For the channels of the oscilloscope, I recommend to have the speed command, the actual speed, the IQ current command, the IQ actual value, the ID actual value, and what is very important, the back EMF voltage output and the total voltage output of the inverter. In this case, orange. For demonstration purposes, I have set the KE factor to 0, and you can see the voltage, the total voltage is provided while the back EMF voltage is set to 0. So what is our goal on this page speed? We can see the output of the current controller. The output of the current controller is the VQ and the VD voltage, which will be our total voltage. But we require the KE factor for the back EMF voltage output to help the general PI current controller output. So how do we do that? Basically, it's very simple. We are gonna rotate the motor to about roughly 1000 RPM, and then we are gonna disable the inverter using the disable the button, and immediately re-enable the inverter again, while having the motor control set to initialize using torque command. This is very, very, very important for this test, because we want to enable on torque command with torque 0. So we just provide the back EMF voltage for the motor to run freely without any braking or accelerating torque. If you would be enabling with speed control, the motor controller will try to brake the motor to 0 RPM immediately after initialization. But we do not want that. We want to have a torque-free, free-running motor when we enable the motor controller. Going back to the oscilloscope page, we have to configure the oscilloscope page now. We set a trigger to go, we set the edge to rising level, and we set the level to 0. This will enable a measurement as soon as we enable the motor controller. For capturing, I recommend 2000 buffering points, a normal run operation, meaning it will do a measurement each time the trigger level has been activated. And for the speed time per division, I recommend 10 milliseconds because we want to have a close view just after the enable. And I recommend to use a pre-trigger of 25% so that the enable process will be centered a bit more and we can see more. Okay. After we have done these configurations, you can start the oscilloscope measurement. You can enable the drive. I recommend a slow RPM speed for the beginning, for testing, and then with the disable button, you press it twice shortly after another. Meaning it will trigger a measurement when we enable. We do not see much because the RPM speed was quite low. Now we go up to 1000 RPM while the drive is enabled. The RPM speed is roughly at 1000 RPM. It can be lower, it can be a bit higher. It doesn't matter. It's just that we need a high rotation during the enable process. You will hear a loud clicking noise. That is because just after the enabling process with torque 0 control, you will have a small AC current flow. In this case, about 67 ampere. That is because the PI controller is lacking the BackEmf pre-control it requires to smoothly enable on a spinning motor using torque control. So let us test now. So we're gonna provide a small KE factor of, let's say, 20 voltage per 1000 RPM. I'm gonna make this a little bit bigger so we can see this a little bit better. And then we just repeat. Enable the drive, start, disable and enable again immediately afterwards. I'm gonna stop. Now we can see how in red, depending on the factor we have entered, there is a pre-control output. And the AC current spike is a little bit lower because there is already a pre-control. So what is our goal? Our goal is to configure the KE output to have a voltage BackEmf output in red, which will match the total voltage output. Okay. At the moment we are about 50%. Okay. So we go up 50%. I enable. I'm gonna spin up the motor again. Disable, enable. And as we can see here, we have already almost matched the total voltage output with our BackEmf voltage pre-control output. And as you can see, the current output is almost 0. So we almost have it. So we go up another 3%, 3 volt. We enable the drive. We enable the measurement. We go up to 1000 RPM again and repeat the process again. And now we can see the BackEmf voltage output almost exactly matches the total voltage output it requires to enable with zero torque at a specific RPM speed. Of course, you can fiddle around for a while, but I'm already very happy with this kind of result. So let us have a look at this value. 43.00 volts per 1000 RPM. We can go and save. So let us just fact check this value. We open the Emrax datasheet. And what does Emrax say? Emrax says induced voltage RMS per 1 RPM of 0.0300. And if we open our calculator, 0.03 multiplied by 1000 multiplied by the square root of 2, 42.42 volt per 1000 RPM, which is almost exactly what we have estimated using this process. And we have confirmed that it is a medium voltage motor and not a low voltage or a high voltage motor, which is great. So I hope this small video of trying to figure out the back EMF voltage of this motor helped you, and yeah, all the best and happy controlling. Bye.